So we will continue with our discussion on system simulation when you have multiple unknowns, that means more than one component is present. So we will revisit the truck problem. So we will solve the same problem using the Newton-Raphson method for multiple unknowns. Okay, it is going to be problem number . Okay. So for the sake of completeness we will go through the problem again. So a truck is climbing up a hill road very slowly. So given below the characteristics, that is the torque speed characteristics of the engine and the torque speed characteristics of the load. The truck continues to drive uphill at the same transmission setting, so it is going at the same either it is in the second gear or third gear or whatever. So using Newton-Raphson method determine the operating condition of the truck. So it is a watered down version of the earlier problem where I asked you to draw the information flow diagrams, two information flow diagrams using successive substitution, solve using both the information flow diagrams, examine the stability and all that. Having done all that, now there is no need to go through all that. Now you solve it using the Newton-Raphson method for two unknowns, right. So you have to rewrite the characteristics in terms of F1 and F2. F1 and F2 are functions of t and omega. You have to open out a very wide tabular column and then it is going to take some time, it is going to take at least half an hour. So I will help you with the iteration, but after 5 minutes I will take this slide off and then we will use I need to use the full board. Okay. So all of you first write down F1 F2, take dou F1 by dou t, dou F1 by dou omega, dou F2 by dou t and dou F2 by dou omega. Many of them will be constant, one of the four will keep on changing with iteration, okay, and then you can use any technique for solving a 2 by 2 system. Okay. So in this case okay. Now I intentionally made a small error. Huh? Minus where? Huh?
Minus F1, minus F2.
That's it. Correct? We are expanding the solution around x of I, right? x1 of I, x2 of I, x3 of I at I plus 1, and then we are cancelling that x I plus 1 equal to 0. You remember? That is how you get this. Deepak, yeah. No, without minus it will go in the other direction. How? No. No. You need a minus sign somewhere. You will give the wrong correction, right? So this is a so initial guess. Yeah, let us all start with I worked out the number, so I will tell you the initial guess. 440, huh? Yeah, you have noted down, right? So Ti omega I, Ti plus 1 yeah. So it has got 12 columns. As of now the number of rows is unknown, right. So this is the kind of problem which you can expect next Monday, not next Monday, the subsequent Monday. I will not ask us one component system, right. So you need patience. Hopefully I don't give you a problem in which there is log and other things, right. It's possible to give. I can give you a heat exchanger where MCP delta T is equal to UA LMTD and I can make you go round. I have done that before. So okay, so let us start with this 400. So you have to evaluate. Let us start with iteration 1. So please tell me what is F1? Minus 145, correct. F2 we have to get the components of the matrix, this fellow, because 3 guys in this will behave properly, all it they will remain the same in all the iterations, correct. So dou F1 by 1, good, all of us are happy, right. What about this fellow? He is also 1. What about this guy? No. I wrote it out in a deliberate sequence such that all the 3 are invariant with respect to iterations, but the 4th fellow is not, is going to give trouble. I mean he will keep on changing. So 0.6 omega minus 30. So now you have to say T is equal to 400. Now you have to evaluate these 1, 1, minus 40, right? Any problem? Good. Yeah. Yeah. There is a minus already, right? So good. So the minus of minus. Rajesh, got it? Already doing. Okay. So what about the fourth fellow? Minus 6, huh?
Minus 6.
Minus 6. Parameshwar, what's the problem? You're not able to see. The trouble is every iteration you have to solve a 2 by 2. Suppose I give a 3 component system. If I give a 3 component system, one problem will be a 3-hour exam. Because one shot you will not get it, right? Because you are iterating. So that will be a 3-hour exam. But it will become a test on whether you do algebraic manipulations properly or not. So, but I have to test you. A 1 component system is very trivial. A 3 component system is very tough. So I will test you on a 2 component system. Alright? That is a fair game. Yeah, so F1 we can put minus 145, minus 40, dou F1, dou F2 by dou T, correct? Dou F1 by dou omega minus 6. Error is of course so it is good to do in the class because it becomes a lecture come tutorial, right. So you because once you go through 1 or 2 iterations you know how to do it, it becomes very fast. There is only one component in the 2 by 2 matrix which has to be evaluated. 3 things have to be evaluated each time, F1, F2 and this thing. See, you can stop the iterations either when this is not changing, or you can stop the iterations either when t and omega are not changing, or F1 and F2 become close to 0. Yeah. Eventually when F1 and F2 are close to 0, this fellow also will become stationary, these 2 fellows. Okay. So what do you get, delta T and no delta T is 61, 271, too much, plus both are plus, so E 671 and 61 is too much. What is the error? What is the error?
73,900.
73,900. If you look at this, it looks hopeless, but this is Newton-Raphson, it will work, it has quadratic convergence, right. So let us start with the iteration number 2, 671, F1 and F2. 4th and 5th iteration it converges, do not worry, I have done it. Yesterday I have done it and I have this. Okay, so I want you to do it. F1, F2, 132.3, 132, zero, but do not be too happy, only one of the 2 fellows is 0. Okay, so then good, 6.6. it okay? Huh? 588. Check, send it. Check it out. Deepak? Yeah. Mridula, what is the error?
6,900.
6,900. Okay. Not bad, right? Error is becoming decent. It's not decent enough, but still. Quadratic, let's see, 588.31. So actually if you see, it is not so difficult, but it requires patience and perseverance. I mean, so you should not, even if you make a mistake in one iteration, if your basic algorithm is right, it will get corrected. You may take 5 minutes, you may take 2 more iterations, but it will eventually converge. So long as you have not made any mistake in writing this out. Suppose one of the derivatives you make a mistake, or somewhere f1, f2 you make a mistake, it goes to some other arbit value, it will correct itself after some time. Okay. So 588, but all the good work you have done in the previous iterations will simply vanish. If you make a mistake, then again the solution will go somewhere, right. F1 is now 0.03, 2.09, right. See, look at how f1 is falling, f2 is more or less well behaved. F2 is a linear equation, right, t is equal to 11 omega, it will not misbehave. This fellow is because he has quadratic terms, minus plus 175 is there, 1 minus 30 omega is there, plus 0.3 omega square, he can go up and down, okay. But already I think we are able to see some, we are tasting some success because f1 is going down. I know for a fact that it converges because I already done, in the next 2 iterations it will converge, right. So what do you get now, ti plus 1, 574, is it right? How many of you have completed 3 iterations? 2 iterations? Yeah, you please check out your speed. I would expect you to finish this problem in 30 minutes in the exam. So if I give this question, I will give 1 or maybe 2 more questions which will take 10 minutes. This probably will carry 60% of the marks or something like that, and I expect you to finish it in half an hour. Of course, I know that if dou f1 by dou t and dou f1 by dou f1 and by dou x1 and dou f2 by dou x2 are more involved, then it takes a longer time. Here it is simple function, it will be more involved, the calculation of derivatives will take a long time. Vishwas, did you get it? You got it? What is the error now?
I got slightly different values.
Yeah, then we will check. I might have made a mistake. Is it correct? Raghav?
Correct.
This is correct. Then
Yes.
tell me, report the error.
217.
217?
205.
205.
Okay, so we will go to the 4th iteration. 574. .127. What is this now? F1? 0.5? Sampath? 0.5. So we are almost there. F2? He is slightly going off now. 0.08? F2? Yeah. Derivative?
1.308.
Okay. 1.31. Deepak. Sendil, did you get it? Vaibhav. Doing. Arun. What happened, Deepak? Which one? F? Yeah, it's all right. It depends on how many decimal places you save. It's close to that. Vikram, did you get it?
Slight difference.
What?
The second one I'm getting slightly different. F2 I'm getting slightly different.
You are not getting 574 and 51?
No, I got that. F2 is slightly different.
F2 I got 3.75.
No. 3.
Huh?
It's not 0.
It's not 0.08, I think so. I got 3.75. What are you getting? Parameshwar, Sampath?
2.
0.02.
Yes, sir.
Minus? Minus 0.2 or 0.2? So for this value, what do you get now? Okay, for 574.3 and 51.85?
It's 52.2.
Huh? You want to change this? 50? This is correct? Then this is 52.18. This is 205 or? Okay, we will stay with that. This is okay, 0.5, F1. So what is F1 with this? You got it, Mridula? 0.53. Plus, both are plus. This follow is 1.31. Okay. Now you get the next one. I think we will stop with this. Got it? No? You are not doing? I think you should bring calculator, otherwise you will miss the. I want you to make mistakes in the class. It's better to make mistakes in the class and learn instead of making mistakes the day of the quiz or. Akshay, what's up? Yeah, now complete this. What are you getting? 5? 573.6. Error 0.20. We will just go for one more iteration because it's still not. So 573.6. Yeah, just go for one more iteration, 5 minutes, and we'll. So since it has already reached this level, it is not a very acceptable for it has to go down further because it is a sum of two things. It should go down a little bit. It will. Okay. Yeah. What are F1 and F2 for this? 0.05. Yeah, that means already we have reached home. I mean, so we have reached our destination. You can stop with this, but if you want, you can. Suppose I give you a condition. Usually, I will say decided on appropriate stopping criterion. You can decide a stopping criterion based on Fi, F1 I plus 1 minus F1 I divided by Fi or divided by Fi modulus must be less than something, and F2 I plus 1 minus F2 I divided by F2 I modulus into 100 must be less than something, or as he says F2 I plus 1 minus F1 I whole square plus F1 I plus 1 minus F1 I whole square, that should be less than something norm. All right. Okay. So if somebody has these iterates, please let me know. $573. What is this? 1.2. Okay. 573.62. 10 to the minus 6 whatever. So we have reached. I can show it on Excel, but you can see the quadratic convergence here. 73,900, 6,900, 200, 0.2, 10 to the minus 6. If you plot, you can see that it will go rapidly. Ashutosh, yes.
F2 and F1 should be tending to 0.
Yeah.
So this itself is the error. F2 and F1.
That's what I am saying. Error you can decide on the basis of several criteria. Normally in problems you have to choose the error criterion. I told you choose an appropriate error stopping criterion.
But the functions will be changing. Functions will increase, it will be oscillating.
Which function will be oscillating?
You're saying F1 and F2 as the error criteria, why to take that as errors?
No, what he is saying, if it simultaneously, if here F2 became 0, but F1 was very bad, but no, both are, when they are, see when this is approaching, this also will go to a low value. Okay, so this is only an additional check. For example, when you use Fluent and solve a system of equation, Navier-Stokes equation, energy equation, you can beautifully converge to a totally wrong answer. That is, your momentum equation 10 to the power of minus, continuity equation 10 to the power of minus 4 residuals, energy 10 to the power of minus 8. Okay, it is converged, but you converge to a highly inaccurate solution. So we need additional checks. What do you do normally as a heat transfer, when you are solving heat transfer problem? I will ask my students to check whether energy balance is satisfied. If it is steady state, energy in the sum of energy in whether it is equal to energy out. If it involves mass flow, mass in minus mass out divided by mass in modulus into 100. There are additional checks. Okay, when you are solving a transient problem, this alone may not suffice, because if you have an extremely small time step, you are simply not allowing the variables to change, and then you say 10 to the power of minus 6, 10 to the, it is meaningless. When you have microsecond or nanosecond as your time step, you are not just allowing the variables to change. If you are having that such a kind of time step, you should allow it to run it for million time steps. Okay, so once you start solving problems, once you do your project, whether it is BTech or MTech or PhD, or then when you get into this business of computing, then you will realize that it is not so straightforward to decide on the stopping criterion and all that. Multiple checks have to be there and so on. That is why we have grid independent study, you have validation, there are so many things which your solution has to satisfy. Alright. So this gives you an idea of how to use Newton-Raphson method for multiple unknowns, right. So we will go to system of linear equations where several variables are involved. Any doubts up to this? Okay. People who are excited about this can solve the fan and duct problem. I have the solution. It converges within 3 iterations, 3 or 4. Okay. So this is what your Simulink of MATLAB is doing. How many of you are aware of this Simulink tool in MATLAB? You can put various components and model it together. Of course, it is a classroom environment, I can demonstrate only for 2 components. But if you write out the equations for each of these components and put together, some solver like this may be running in the background. This is what Simulink is doing. So if you write a code, if so many engineers develop this and this, then you can make it a product and make people buy this. Of course, as a user we want to solve some engineering problems. So whether it is in fluid mechanics or basically a lot of these things will come in ventilation design, ducting systems. You want to design air conditioning system for this 3rd floor of ICSR. Fan duct characteristics will come. Then the chilling load, I mean the chiller performance with the load. Suppose Balaji takes a class with 80 students, next class somebody takes with 40 students, what is the load for 10 o'clock, 11 o'clock, 11 o'clock, 12 o'clock, you have to calculate all that. How is ambient temperature changing? Diurnal variation, how is ambient temperature changing with season, all this, so it gets messier and messier, okay. But this is essentially what, this is the engine of Simulink. The engine of Simulink is something like this, the funda behind Simulink is this, okay. There is also, Europeans use something called Modelica, that is also available on DC++ or Modelica is a very powerful tool. I think there must be an equivalent of Simulink in open source, right? What is that? Spelling? Yes? Skylab is like MATLabs. I will write it for the benefit of other students. Spelling. Somebody should stand up and spell it out. SC? Ah. Okay. Okay. So, please make a note of this. If you are doing your projects, if you are a protagonist of open source, you can use this. Otherwise, you will use a illegal version of huh? So, please be reminded that you are still doing simulation, we have not come to optimization. Simulation itself we have so many hiccups, right, multiple systems, there are, you have to learn methods to do simulation, optimization comes later. You are, by solving all this you are getting only the operating point, we have not come to the point where we are able to say whether it is a best or whether it is a most desirable or not. It has taken so much time for us to get the operating point itself. System of linear equations, in thermal engineering where do we encounter examples? Fluid flow circuits, right, from a source it comes through one pipe, then it branches out, it goes into various branches, you are trying to find out the mass flow rate going through various components, okay, and then pressure drop characteristics. So, fluid flow circuits. Then chemical reactors, these are all linear systems. For example, in a fractionating column the total amount of petroleum products must be equal to whatever is sent in plus whatever minus whatever is left out must be equal to sum of naphtha plus diesel plus kerosene plus blah blah blah. You set up a system of equations and try to find a, you may eventually try to solve an optimization problem. What should be the optimal product mix so as to maximize my profits? That is the eventual problem. So, it will pose a, it will be mathematically posed as a system of linear equations. Then conduction heat transfer, where do you get in conduction heat transfer? Okay, I have a composite insulation, okay, I have material A, okay, A, B, C, D, E, F, G. So, there are various materials of thicknesses and thermal conductivities. So, I have a T1 infinity here, I have a T2 infinity here. I will write it out, write all these out as resistances in series and parallel, I will combine, okay. So, this is one possibility. So, like that there are various examples in which you can linearize and have a system of linear equations. So, we need to know how to solve a system of linear equations. So, this has been taught to you ever since you came to the 9th standard, right. So, solving a system of equations involving two components or two variables is very trivial. Okay. So, let us consider a simple two variable problem. Let us go back to our high school days and I have some specific example 2x plus how many ways are there to solve the system? How many ways are there to solve the system? You can do elimination. Okay, you can use substitution. From the first equation you can take 3y is equal to 13 minus 2x, put it in the next equation and solve. Method number 1. Method number 2, matrix, you can solve using matrix. Method number 3, you can solve graphically. So there are, so for a two variable problem it is very trivial, we learnt it long back. Okay, if you want to solve it in a, okay, the solution is 2 3, right, correct. Okay, so substitution, these are all very elementary. Okay, so let us look at this matrix inversion. So the whole system can be written as Ax equal to b. So the vector x what you write for two variables can be extended to any number of variables, right. So in our case correct. So, but D is the determinant, yeah, you can complete it, hopefully it gives 2 3, right. Otherwise it will be major embarrassment. Huh? Okay, let us see. $26. Thank God. Okay, so this is, now we have this. So if you have a system of linear equations for n number of variables, it can be used. Oh, Cramer's rule. You want me to teach that or? How many of you don't know the Cramer's rule? Good. Okay. So you have to take the determinant and change the first row by the, if you want to solve for x1, change it by a1, a11, a12, a13, and This is not a course on linear analysis anyway, but matrix inversion is important. So up to 100 variables you can invert, generally it will be stable, okay. But if you have more than 100 variables, matrix inversion is not. Sometimes the matrix could be singular. If a matrix is singular, the determinant is 0, okay. If the determinant is 0, it cannot be inverted, it leads to a lot of trouble, that is one. Or sometimes you have infinite number of solutions. In those cases it is imperative that, and also in other cases where the number of variables is more than 100, inversion is not a good idea. People have developed other techniques like Gaussian elimination, okay, LU decomposition, Cholesky decomposition, Jacobi method, Gauss-Seidel method. So there are so many methods. So this could become a 45-hour course on linear analysis and all that. But for this course the Gauss-Seidel method is extremely popular, it is eminently programmable, okay. Therefore we look at the Gauss-Seidel method. Before that we will see how this, even a 2 variable problem, can give trouble. What that is, where are the situations where you can have singular and ill conditioned systems. So I have taken a specific case, for example 2x plus 3y what about these two? Huh? No solution, why? They are parallel lines, man, they will never meet. What is D? Huh? D is equal to 0. This is a singular system. Okay. So this is A. So A minus is our example, which is well behaved, right? Okay. Oh, okay. Call that A. Call this B, C, whatever. B 2x plus 3y is equal to 12. They are same, therefore infinite number of solutions. D is equal to 0. This is also a singular system. Okay. You can also have a third category. It is getting late, I want to show it on the Excel, but still okay. You can have 2x plus 3y the determinant is close to 0, this will give hell a lot of trouble. The two lines will be very close to each other, you do not know exactly where the two lines intersect. This is called a ill conditioned system, okay. So but how small is subjective. For certain types of systems this small is alright, this value of D, but certain types of systems this value of D is not alright. So D is small, therefore two lines very difficult to locate point of intersection. in tomorrow's class we will first 5 minutes we will just plot this on Excel and see why, okay. So this is basically ill conditioned system. If you have several variables and the system is ill conditioned, round off errors will give lot of trouble. This round off errors will propagate because the d is small, and it will prevent you from getting the true solution, okay. So in tomorrow's class we will just complete this, and I will teach you the Gauss-Seidel method, which is a very powerful technique. We will solve a 3 variable system using the Gauss-Seidel method.